Good morning, chemistry students. This is your Chapter 8 Day 1 notes. So we will be starting on your Chapter 8 outline at the review, and we're going to go all the way through the other symbols used today. So you'll see that your outline starts with review, and it starts with the review of law of conservation of mass. And we actually have not specifically talked about this before, so we're going to talk about it for the first time here. Any conservation law is always the same in science. Conservation means to save. So when we're talking about conserving mass, we're going to be talking about the fact that the mass before a reaction is the same as the mass after the reaction. Okay? Now, when we're balancing equations, we're not going to measure mass, but remember the mass of in a reaction is going to come from the mass of the atoms. So for us, for the law of conservation of mass, the law of conservation of mass says that matter cannot be created or destroyed during a chemical reaction. And oftentimes we put the word normal in there because nuclear reactions are sometimes a little bit different, okay? Which we won't ever talk about, so. Therefore, mass cannot be created or destroyed either. During a chemical reaction. Now, this is going to be important. You'll see this on ChemQuest 37 when we are balancing chemical equations, which is what we're going to be learning to do in this unit, okay? This is going to be important because we're going to count atoms. So for us, okay, you're going to become atom counters. And basically what you're going to do is you're going to make sure you have the same number of atoms on the reactant side as you do on the product side. Okay? And the reason you have to do that is because of the law of conservation of mass. We can't create matter or destroy matter. We can't create mass or destroy mass. So another way that we can kind of think about this law of conservation of mass is that atoms cannot be created or destroyed. And so when we're balancing equations, we're not going to measure mass and do math to figure out if they're balanced. We're going to count atoms. And as long as we have the same number of atoms on the left-hand side of our equation, the reactant side, as we do on the right-hand side of our equation, the product side, then we'll know that we have followed the law of conservation of mass. So again, there'll be a little bit more about this as we get into our outline a little bit more. So next we want to review molecular compounds because Mrs. Krumscharter, I am a pain in the butt. And when I give you equations to write and balance, I'm going to give you words and sentences. So you need to remember how to write the formulas for molecular compounds and ionic compounds. So we're going to start by reviewing a molecular compound. Again, we're going to know it's a molecular compound because it's made of two nonmetals. Now, you need to remember where the nonmetals are on the periodic table, right? So I should have a periodic table I can pull in here. There we go. Right? Remember, our nonmetals are pretty much this. Oops, I've got to put it down and then I'll destroy it. Remember, it's this kind of heavy stair-step line, right? That's our dividing line between our metals and our nonmetals, and this side are our nonmetals. Okay, so molecular compounds are made of two nonmetals. What's the name for the chemical formula? Remember, we can call the chemical formula just a chemical formula, but there are also more specific names. And the more specific name for the chemical formula of a molecular compound is a molecular formula. So what that means is I cannot call the chemical formula of an ionic compound a molecular formula, okay? Molecular formula is specific to a molecular compound which is made of two nonmetals. All right, how to write the chemical formula from the name. This is mostly what we're going to do moving forward through chapters 8 and chapters 9. Okay, so this is the part that's really important that you remember how to do. And remember, for molecular compounds, to write the chemical formula from the name, our prefixes become subscripts. Okay, and we write the compounds, or we write the elements. So we write the symbols in the order, and we can say, how about the same order as in the name. And again, on ChemQuest 35, we when I did the teaching video, if you're kind of struggling with remembering how to do this, then go find the teaching video for ChemQuest 35, because there are some molecular compounds there, and I walk through this, okay? So we're going to write the symbols in the same order as in the name, and our prefixes become our subscripts. Remember, you don't have to have those prefixes memorized, okay? Again, remember, you have this helper sheet, right, that has all those prefixes on it. So you don't need to memorize those prefixes. You just need to know where that helper sheet is. Okay? Next, how do you write the name from the chemical compound? Again, we're going to do this occasionally, but not nearly as often. Right, so this means I've given you the chemical formula. How do you write the name? For molecular compounds, again, we name the elements, or we'll say, how about atoms? Atoms in the same order as the formula, with the second atom ending in "ide." Okay, and again, our subscripts become prefixes. Okay, so remember what was really important about molecular compounds. They're two nonmetals, and subscripts become prefixes, prefixes become subscripts. You don't have to have the prefixes memorized. They're on your helper sheet. Really important you know where your helper sheet is. Okay, so that's kind of our review of molecular compounds. We're going to do the same kind of review for ionic compounds. Again, how do we know that a substance is an ionic compound? It's made of a metal and a nonmetal, or remember, it contains a polyatomic ion. Okay, so it is a metal and a nonmetal, or it has a polyatomic ion. Again, that's why it's super important that you have those 10 polyatomic ions memorized. If you don't have them memorized very well, then you need to find that handout that you got back in Chem 1A that had the list of all of those polyatomic ions. Remember, if it's not a polyatomic ion you have memorized, then it's going to be on your helper sheet. Okay? So remember, you have this helper sheet that has those other polyatomic ions that we may use, okay, that you don't have memorized. So again, that's how we know it's an ionic compound. Again, probably should also review where our metals are. So again, we'll take a look at that periodic table, right? This is our dividing line right here. Right, and these are our nonmetals, which means everything else, these are metals. Okay. Okay, so just like we have a special name for the chemical formula of a molecular compound, we also have a special name for the chemical formula of an ionic compound. Remember, that means that this can only be used to refer to ionic compounds and it can't be used to refer to molecular compounds. The special name for the chemical formula of an ionic compound is a formula unit. Remember, everyone loves our abbreviation for formula unit, right? Our FU. Okay. So again, I can call the chemical formula for an ionic compound either a chemical formula or a formula unit. I could not call it a molecular formula. That would be incorrect. Again, most of what we're going to do, most of what I'm going to ask you to do is I'm going to give you a name and ask you to write the chemical formula. So remember, when I give you the name, there are 4 steps, right? You write the symbols. You write the charges. You crisscross the charges, and remember, it's only the symbol, or sorry, only the number, not the plus or the minus, okay? And then lastly, you make sure it's the lowest whole number ratio. Right? You should be able to kind of rattle that off to me, right? Symbols, charges, crisscross, lowest whole number ratio. Symbols, charges, crisscross, lowest whole number ratio for ionic compounds. Now, about the charges, just a kind of a little review about that, right? I'm not going to write it down, but I'm going to say it to you, and if you have space, you might want to write it down, right? Charges. So when I look at my periodic table, which again, I'm going to pull up for you real quick here, right? When I look at my periodic table, group 1A has a charge of +1. Group 2A has a charge of +2. Okay? Group 3A, right? Tall columns, you should know the charge, has a charge of +3. Group 4A has a charge of +4. Group 4A typically doesn't form ionic compounds. Group 5A has a charge of -3. Group 6A a charge of -2. 7A a charge of -1. Remember, when we're talking about our transition metals down here, then we have to look at our helper sheet. So remember, on our helper sheet, you have this information, right, which lists the element name, its possible charges, and its Latin root. You're going to be given that information one of 2 ways. Remember, with the stock system, it will be the element's name and a parentheses and a Roman numeral, and the Roman numeral is telling you the charge on that transition metal. Or I can have the Latin root in either us or ick. Us is the lower charged one, so you have to look at these and see which is the lower, and ick is the higher charged. Okay, so again, really, really important you know where your helper sheet is to help you with writing these names. Because again, I'm pretty picky about this. I pretty much always am going to give you the name and ask you to write the chemical formula from the name. Your textbook's a little nicer about it than I am, okay? But if it's me, I'm going to ask you to write that name. And then again, we won't do it as often that we have to write the name from the chemical formula, but generically we say that we combine the name of the cation and the anion. Remember, if our cation has more than one possible charge, then we have to name it twice. Okay. I want you to always name it twice to practice. So again, remember the stock system, it's the element name, parentheses, the charge on the ion is a Roman numeral, and then the name of the anion. If it's the classical system, you're going to use that Latin root in either us for the lower heart charged one or ick for the higher charged one as an ending, and then the name of the anion. So that's your review of ionic compounds. The last little review is about your diatomic molecules. These have been on your polyatomic ion quizzes, right? These are molecules that they, even when it's an element, they exist bonded together. Bonded to itself. Right? So our diatomic molecules are Brinkelhoff. Okay? So it's Brinkel, Hoff. And this is how I expect you to write them on your polyatomic ion quizzes. So you might have lost some points along the way for not writing them this way. There are 7 of them. 1, 2, 3, 4, 5, 6, 7. Your other option on polyatomic ion quizzes for how to write them is you can write their names. So you could write bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Oops. Should be an I. Okay. One way or the other to get full credit on polyatomic ion quizzes. Okay. So those are those diatomic molecules. That's going to become really important, right, as we start to balance it. That when we have these by themselves, so not bonded to another atom in a compound, they're existing by themselves, we have to write them as being diatomic. So now that we reviewed a little bit of that information, we're going to get kind of started into balancing our chemical equations. And when we're balancing chemical equations, I'm always going to ask you to start with a word equation. Okay? So before we kind of talk about what a word equation is, I want you to think a little bit about what are some examples of chemical reactions, okay, in real life. Okay? And one of the clues that a chemical reaction has taken place is that something looks different. So, okay, for example, cooking your food, right? Raw chicken looks different than cooked chicken. That's a chemical reaction. Raw steak looks different than cooked steak. That's a chemical reaction. Rust on your car, right? Your car panel looks one way before it rusts, and when it gets rust on it, it looks different. So that's a chemical reaction. The energy from your car battery, so how your car gets that electrical energy from your battery, that's a chemical reaction. In biology, photosynthesis, how plants undergo photosynthesis and create their ATP that they need for energy. Okay, photosynthesis is an example of a chemical reaction in real life, and kind of a gross one, but digesting food, right? The food looks different when it comes in than it does when it goes out. That's an indication of a chemical reaction. So just make sure you have a couple examples of chemical reactions in real life written down on your outline. Again, digesting food, photosynthesis, energy from a car battery, the rust on a car, cooking your food. Those are all examples of chemical reactions, right? Baking a cake, right? The cake batter looks different than it does when you finish up. All chemical reactions involve changing substances, right? We just saw that, right? Our food that we eat is changed. Photosynthesis changes things. Cooking our food, we've undergone a change of our substance. So all chemical reactions involve changing a substance. In chemical reactions, one or more substances, called our reactants, change into one or more new substances, which are our products. In our chemical reactions, an arrow is used to represent that change. So when we kind of look at this generically, we always have our reactants on the left, our arrow to represent that chemical reaction taking place, and our products on the right. In a chemical reaction, bonds are broken and new bonds form. So remember, we kind of talked about two types of bonds back in Chem 1A. We talked about ionic bonds, which are between metals and nonmetals, and they're positively charged cations being attracted to negatively charged anions. And we talked about molecular or covalent bonds that exist in molecular compounds. So those bonds are broken, and we have new bonds that form. What's really important is, although our substances are changing, atoms are not created or destroyed. They are just rearranged. And that's the law of conservation of mass that we started by talking about today, right? We can't create or destroy atoms because we can't create or destroy mass. We can't create or destroy matter. So the only way for those things to be true is that all of the atoms that I start with in my reactants, I have to have the same number of atoms in my products. Now, they may not be in the same compounds, right? Because bonds are getting broken and new bonds are getting formed, but the atoms are all still there, okay? And so you are going to become kind of, as I mentioned, atom counters. That's how you're going to check and see whether or not you have correctly balanced your chemical equations to make sure you're following the law of conservation of mass. Okay, so all chemical reactions involve changing our substances. We have our reactants. We use an arrow to represent that change. We put our reactants on the left. We put our products on the right, which are our new substances. We get bonds broken. We get new bonds formed. We have to follow the law of conservation of mass. For us, the way we're going to follow the law of conservation of mass is that atoms can't be created or destroyed. They're just rearranged. And so you're going to be counting atoms. So, as I mentioned, typically I'm going to give you words to start to write these balanced chemical equations. So we have sentences, a sentence representation of chemical reactions. And again, I'm going to give you an example of one here. Okay, iron reacts with oxygen in the air to produce iron 3 oxide, also known as, which is where AKA comes from, rust. Oops. So this is an example of a sentence representation of a chemical reaction. Iron reacts with oxygen in the air to produce iron 3 oxide. So our goal is to learn how to write and balance this chemical equation. So the first thing that we're going to do with our sentence is we're always going to write what's called a word equation. A word equation, okay, uses a combination of words and symbols. The only symbols it uses, okay, are plus sign and the arrow. Everything else is still going to be words. Now, why do I kind of make such a big deal about this? I make such a big deal about this because your word equation, most times, the ones I give you are often going to be like one sentence. But in your textbook, oftentimes, these equations, okay, these sentences are going to be a paragraph. And there's oftentimes a lot of extra information in there. So the purpose of the word equation is that you can get rid of extra information that's not really that important. To balancing the chemical equation. Another way that we could say that is that it allows us to focus on what's important. And typically the first thing we're going to write when we do our word equation is our arrow, because one of the things that will also happen is sometimes your textbook is trying to be tricky. Sometimes they'll start by saying hydrogen peroxide is produced by the reaction of hydrogen and oxygen. Well, in that case, hydrogen peroxide is actually a product, not a reactant. So sometimes there's a little bit of trickiness, okay, trying to kind of get you caught and not paying attention and have you put something on the reactant side that should be on the product, or the product that should be on the reactant side. So typically when you do a word equation, your first symbol will be the arrow, okay? So we want to look at some examples of this. And for our first example, we're going to use this sentence from over here. So we're going to use this iron reacts with oxygen in the air to produce iron 3 oxide, also known as rust. Now, I'm not going to rewrite it. Perhaps you would like to, okay? But that's our sentence. So the first thing, again, we're going to do is we want to draw our arrow so that we can put things on the correct side. And I'd put your arrow towards the middle, right? Because I'm going to put some stuff on the reactant side on the left. I'm going to put some stuff on the product side, which is the right. So iron reacts with. So does that make iron a reactant or a product? It's a reactant, right? So it should be over here. So I'm just going to use it in words, right? That gets to stay a word. Oops, sorry, wrong way. So iron reacts with oxygen. What's the reacts with going to become? Right? Reacts with is going to be our plus. So again, we might kind of want to make a little note up here, right? That reacts with is typically going to be a plus side. Okay? And oxygen in the air. Again, there's where I'm giving you some extra information. Is the fact that the oxygen comes from the air really important to balancing this chemical equation? Nope. It's extra information I can ignore. What's important here is that oxygen part. So reacts with, my other reactant here is going to be oxygen. To produce, right? So our arrow is going to be to produce, or producing, to yield, or yielding, right? Those are the words I'm going to look for arrows. Here it's to produce. Iron 3 oxide, also known as rust. Again, extra information. I don't have to know, and I'm not going to put that it's also known as rust. I just know that my product is iron 3 oxide. So over here on the product side, I'm going to write iron 3 oxide. That's my word equation for that sentence. So we're going to look at 2 more examples. So you're going to have to make 2 more examples fit in the space that you have. Okay, so our next example, here is our sentence, right? Because I told you I'd give you sentences. Hydrogen peroxide, and I would encourage you to write the sentence as well, reacts to form water and oxygen gas. So that's our sentence. Again, we want to take this to a word equation, so first thing I'm going to do is I'm going to put my arrow towards the middle. And, okay, my arrow here is the to form, right? My to form is becoming my arrow. Hydrogen peroxide reacts. So that means hydrogen peroxide is a reactant. So I should put it on the left. Reacts to form, so there's not another reactant here, to form water and oxygen gas. So one of my products is water. The and, again, remember, my only symbols can be plus signs and arrows. So it's going to be a plus sign. So this and became my plus sign. And oxygen gas, and I don't even need to bother with the gas. Again, that's kind of extra information. All that's important to me is that it's oxygen. Okay? So that is my word equation for this. So here's our next one, and I'll give you a moment to see if you can, well, it won't be a good one to try, sorry. So So our next one is methane is burned with oxygen gas from the air producing carbon dioxide and water. So again, I want to make my word equation. So again, I'm going to have my arrow and producing, right, is what became my arrow this time. Methane is burned with oxygen gas from the air. So that's my reactant side. So one of my reactants is methane. Is burned with oxygen gas, so that means I need a plus sign. And again, all that's important to me here is the oxygen. So again, the with became my plus. Okay, producing carbon dioxide and, that's a plus, water. So again, my and became my plus. So that's another example of a word equation. So again, our steps are so far that typically you're going to have a sentence or paragraph that represents your chemical reaction. The first thing you're going to do is write a word equation. Only symbols in your word equation are your arrows and your plus signs. The purpose of this word equation, it's going to allow you to focus on the parts that are important for continuing to write and balance our chemical equation. So we want to kind of get started a little bit today about chemical equations. We're going to start with our definition of a chemical equation. In a chemical equation, an arrow separates the formulas of the reactants from the formulas of the products. So notice the difference between our word equation and our chemical equation is now everything will be symbols. What were words in our word equation will now become symbols. Now, chemical equations communicate more effectively. What I mean by that is, for example, the word water, right? The word water, there's different words for water in different languages, right? In French, it's l'eau. In Spanish, it's agua. Okay? So, writing the formula for water, H2O, the formula for water is H2O no matter where in the world you are. So there's no opportunity for a misunderstanding or a mistranslation of what we're talking about. And our chemical equation uses chemical formulas. So our words are going to become chemical formulas. And again, what that means is that you must write these correctly. Which is why in our review section we reviewed how to write the chemical formulas for molecular and ionic compounds. With our word equation, our goal is to write this balanced chemical equation. The first chemical equation we write is going to be called a skeleton equation. So in our skeleton equation, it's a chemical equation that doesn't tell the relative amounts of reactants and products in the reaction. Basically, a skeleton equation is an unbalanced chemical equation. In skeleton equations, sometimes the state of matter is indicated. So again, it's typically as a subscript, but you might see a subscript S, and I use a cursive S because otherwise it starts to look like a 5 sometimes. L for liquid, G for gas, and then AQ, which means aqueous, which means that the substance is dissolved in water. Now, I won't count it wrong if you include the states of matter, but I also won't count it wrong if you don't have them. When we get to the last section of Chapter 8 and we start to talk about net ionic equations, then you will be required to have your state of matter. But for the most part, I don't care whether or not there are states of matter in your skeleton equations and in your balanced equations. So again, we kind of want to look at our example that we were doing. So we're going to go back to this first example. The iron plus oxygen yields iron 3 oxide. So again, you're still going to be given a sentence most times, and the first thing you'll write is your word equation. So I'm going to do that word equation here. So it was iron, plus oxygen yields iron 3 oxide, right? So kind of our steps to get to a skeleton equation, right, is we're going to first have taken our sentence and we're going to write a word equation. Next, we're going to write a skeleton equation. So that's what I'm showing right now. Here's our word equation. Now we're going to make it a skeleton equation. So now the things in our words are going to become symbols. So my symbol for iron for my periodic table is Fe. Again, eventually I'm going to balance this. So I want to leave space in front of my chemical formulas. So if you just get in the habit of that right now. Now, oxygen. Now remember, oxygen is O, but it's one of those diatomic molecules. So I have to write oxygen as O2 because it's not bonded to anything here. Here's my arrow. Now again, I have a compound here in iron 3 oxide. Is this ionic or molecular? It's ionic, it's a metal and a nonmetal. So I have to do symbols, charges, crisscross, lowest whole number ratio. My symbol for iron is Fe. I know its charge is +3 because that's what the Roman numeral is telling me. My symbol for oxide is O. Oxygen on my periodic table is in group 6A, so it has a charge of -2. I crisscross down just the numbers, and I get Fe2O3. So this, what I've just written right here, this is my skeleton equation. It's not balanced yet. It's just a skeleton equation. What is a catalyst? Sometimes our reactions use a catalyst. A catalyst is a substance that speeds up the rate of reaction, but is it used up? So what that means is it's still there after the reaction. Because of that, technically a catalyst is not a reactant or a product. So we can't write it on either the reactants or the products side of the equation. The catalyst just makes the reaction happen faster. And so because it's not a reactant or a product, a catalyst is written over the arrow. So that second example word equation that we did back here actually requires a catalyst. This hydrogen peroxide reacts to form water and oxygen gas. So we're going to go ahead and take that one to a skeleton equation. So again, we have hydrogen peroxide. I'm just going to put my word equation here first. Right, and this is, I'm just copying back from over here. Okay. Water plus oxygen. And we'll add the catalyst at the end. So, hydrogen peroxide. Hopefully, most of you know the formula of hydrogen peroxide at this point, right? It's H2O2 arrow. Water is H2O. Oxygen, right, is diatomic, so it has to be O2. And I'm going to make my arrow a bit longer so I have a little bit more room to write on it. The catalyst in this is manganese oxide. So I write the manganese oxide over my arrow. So that's how you indicate a catalyst. A catalyst will be written over the arrow. And again, it's just there to make the reaction happen more quickly. All right, there are also some other symbols that are used in chemical equations. On page 206, table 8.1, you have symbols used in chemical equations, and I have a chart in your outline already for you. Here is that chart. And basically what I'd like you to do in your chart and your outline is kind of copy this. Now, pay attention. My picture's not very good here, but there are a couple of these over here that you kind of need to fix. I want to say it might be these because I didn't have a way to type that up. But basically what I want you to do is kind of copy this chart into your outline. And that brings us to where we're going to stop for today. So remember in review when we're going to start writing and balancing chemical equations, okay? And again, typically you're going to be given a sentence, and from that sentence you're going to write a word equation. The only symbols in your word equation are plus signs and arrows, and we do that so that we can kind of get rid of the extra information and really focus on the parts that are important. After we have our word equation, our next step is we're going to write a skeleton equation, which is an unbalanced chemical equation. But now in our skeleton equation, everything that was words is going to become formulas. And that's where we're stopping for today. Have a great day. I'll talk to you tomorrow.